right, friends, we are now on number 2. This problem is about manufacturing making wooden desks and tables. This one's a little bit different because we have different restrictions. So now we're assembling, buffing, and crating both tables and desks. And then we have a limit on the number of hours of assembling, buffing, and crating that we can do. And there's a profit. Now we're talking about profit, and we want to maximize the profit. For those of you who don't know, assembling just means putting together. So we're putting together the desks and the tables. Buffing, sometimes that's some confusion on what buffing is. When you refer to wooden products, when you're buffing something, you're making it so that it removes all the splinters, all of the parts on the wood that could hurt you. So that's what buffing is. It's not making the wood stronger. And then crating means that you're putting it inside a container to ship that actually will not destroy it. So I had a student get really confused one year, didn't know what half of those words were in terms of this problem. So hopefully now you know. The more you know. First thing I want to do, figure out what type of problem it is. Is it a maximize problem or a minimize problem?
Maximize.
Maximize. What are we trying to maximize?
Profit.
The profit of what? Okay, so this is where things get a little bit tricky. Maximizing profit of. So my X is, be careful. It's not dollars. Because I already know, so this is the thing that students will get confused. They'll say, oh, well, it's dollars per desk. Well, that's already established. It's $3. So X is the number of desks. And then the Y then is the number of tables. Well, then what about that profit bit? What are we trying to do? This one, we can actually do one of the things that we did later on in the example from the previous one. We can actually take care of that right now. We can actually get the maximizing function, that f of x comma y. For each desk, how much do I make profit?
3.
So that's going to be $3 per desk plus $4 per table. So this equation here for maximizing, this actually incentivizes us to make more tables than desks if I have the exact same options on both. We don't need to do anything with this yet. We just need to know when we get finished with our critical points, that's what we're going to use. Again, as I talked about in the last problem, we're going to have our columns. So X is desks. And then Y is tables. Now, with my highlighter, I'm going to go through and find all of the things that are restrictions. So I have a restriction with my hours of assembly. So I did that in yellow. In blue, I'm going to put the hours for buffing. No splinters on these. And then crating. So that means I have 3 different restrictions, rows. So I'm going to have an assembling row. I'm going to have a buffing row. And I'm going to have a crating row. How many hours does it take to assemble a desk?
2 hours.
So 2x. How many hours does it take to assemble a table?
1 hour.
So 1y. And how many hours do you work with assembling? 14. So inequality-wise, what's going to be, because I can't use more than 14 hours. So it's going to be less than or equal to. What operation do I want between my x and my y? Because I'm combining them. What about buffing? Plus is less than or equal to Yep. And then for crating, 1x plus is less than or equal to, okay? And then just like we did in the previous problem, we're going to solve these for y to graph. If you notice, on the last problem I was talking about how sometimes students mix up the values. Sometimes students on this problem will try and do assemble as x, buff as y, and then crate as z. They try to bring in a third variable. And it doesn't work because there's only two variables. We know how many hours it takes to assemble buff and crate. We don't know the number of desks that we need. So that's a good way to kind of check to make sure, oh, I don't know the number of desks, I don't know the number of tables, but I know the hours that it's taking. So 2x plus y is less than or equal to, oh, I do this in a different color. My graphing. And then 3x plus 3y is less than or equal to 30. So you get y is less than or equal to negative x plus 10. So I got y is less than or equal to negative 1/2 x plus 8. So now I can graph these. And then where am I going to shade on all of these? Below, yeah, you're going to shade below on all of them. It's all less than, so you're going to shade below. The test point 0, 0 will work for all of them. I'm going to go by ones on my graph. There we go. So light blue, 14, down to right 1. Then connect using straight edge. Then I shade. Now green. Is that 10? Connect that and shade. After you do 2, you might see where you think the solution might be. It's a reasonable guess. Sometimes the point doesn't quite match up though. Oh, I need to shade blue. There we go. And then my purple, plus 8. All right. So after you shade all three, you have to be really careful because your critical points are where all three restrictions match up. So you have to be careful. I circled the three areas on mine where they all 3 points or all three restrictions match up. And I'm not going to do 0, 0 because we know that that's not going to give us the maximum. So for the maximum profit, remember that from earlier, that was that f of x comma y is equal to 3x plus 4y. So my critical points for this problem are 0, 8, 7, 0, and 4, 6. And what do these mean? Well, x was the number of desks. Number of desks. And then y was number of tables. So now when I plug in each of these, I take 3 times 0 plus 4 times 8. So that's a maximum of what? $32, yeah. And then 3 times 7 plus 4 times 0 gives us a maximum of what? 21. It's all good. And then 3 times 4 plus 4 times 6 is 12 plus 24, which is, and that was our maximum. So to get a profit of $36, we make 4 desks and 6 tables. Any questions? Send me an email.